This video is going to look at discussing internal resistance and EMF, electromotive force. The EMF is designed as the maximum energy conversion per coulomb of charge. Okay, so it's the maximum number of joules we can actually supply to each coulomb of charge, and that happens for a power supply when there's no current. This ammeter across here you can see is reading 0, and the fact is I haven't got a complete circuit at the moment. I'm only measuring the voltage that's coming from the supply. You can see from the voltmeter here. What I'm now going to do is I'm going to plug in this lead into the variable resistor that I've got here, and I'm going to adjust the value. I'm going to get a series of readings for current and for voltage. I'm going to plot that as a graph then of voltage on the y-axis and current on the x-axis. So if you take a note of the readings as we go. Okay, so current is 0.44 amperes, voltage 4.72. Current 0.60 amperes, voltage 4.40. Current 0.82 amperes and the voltage 4.03 volts. Current 1.33 amperes, voltage 3.35. And the last one, got a big current, 3.73 amperes, and we've got a voltage of 1.92 volts. Now remember, we started off with just over 6 volts, okay, as our EMF. So we're going to plot that as a graph now. Voltage up the y-axis, current along the x-axis. So we've got our sets of results there. Current in amperes on the left hand side, voltage in volts. There's our 5 sets. Right, and as I said, we're going to plot a graph. And you can see here I've got the graph plotted. Voltage in volts on the y-axis, current in amperes along the x-axis. And the graph we actually get, I know it might not look it, but it is actually a straight line graph. If you plot that using Excel, it would draw a straight line through it. Now the gradient of that graph actually gives us the internal resistance. It actually comes from this kind of relationship here. The EMF, remember, is the maximum, and that's equal to the TPD, the terminal potential difference, plus our lost volts. Now EMF, because it's a particular value, is actually given its own symbol of capital E. Now V would actually represent the terminal potential difference, and IR is equal to the lost volts. That's a small r in this case for internal resistance. Now if I rearrange that, I actually get V equals E minus IR, and I can actually plot that as a straight line graph as you've seen, and hopefully you're aware of the relationship y equals mx plus c. And in that case the gradient M would actually equal to minus r, and the y-intercept would actually be equal to the EMF. Now I've done the calculation based on our graph, right? So I've used these values here, and for that we get a gradient of 1.7, and that's 1.7 ohms. Now that's a pretty typical value for an internal resistance for a supply. Alright, it ranges basically between negligible or 0 up to probably 3 ohms. Right, if you get more than that, you're probably in a mistake someplace. Okay, so 1.7 ohms in my experience, pretty acceptable as an internal resistance for a supply. And if we look at the intercept is actually coming out at 6.1 volts. Well, if we go back to the video, and I took a quick note of it at the beginning, okay, the EMF that was on the power supply was 6.08 volts. So the experiment pretty much confirms what we were hoping for. I actually get the value for internal resistance and EMF from looking at current and voltage from a straight line graph.